For this probability lesson, we are going to focus on what is called a binomial experiment. A binomial experiment has a fixed number of independent trials, and there are only two possible outcomes for each trial. I will usually refer to them as failure, and we'll say that the probability of failure will be the same as F, and also success, and we'll say the probability of success occurring is S. Let's give a very simple example. I'm going to roll a die 5 times. That fixed number would be the 5 because each die roll is independent of each other. My goal is to roll a 1. In this particular case, success will occur 1/6 of the time. Failure will occur 5/6 of the time. One thing you should know immediately is that you cannot have a die roll be both successful and failure when it comes to binomial experiments. That's because those events are mutually exclusive. Not only are they mutually exclusive, my failure and my success better add up to 1. And when that does, that means you've exhausted the whole sample space, which means you have mutually exclusive events that exhaust the sample space. You have 2 complementary events. Failure and success are complementary events. How are we going to compute those binomial probabilities? Well, that's where this formula comes in. To find the probability of, let's say, rolling a 1 exactly 2 times might be the following. So here I'm going to say I want it to success occur twice. I'm going to go 5C2. Why 5? 5 will be the number of independent trials. That's the given n trials. The 2 is the number of outcomes I want to be successful. In this case, I would like to see a 1 show up exactly twice. Well, if I have 5 dice and 2 of them are exactly 1s, then 3 of them are not. And that's where my failure rate comes in. Because each time I had a die that did not roll a 1, then I'm expecting it to be the failure rate of 5/6. I will raise that to the 3rd power because I'm going to go 5/6, and it'll be multiplied by another 5/6 somewhere, and multiplied by another 5/6. So why not just say 5/6 to the 3rd power? And then I'll have it multiplied by 1/6 twice, because it'll be 1/6 times another 1/6. So I am going to use that to come up. It'll be easier understood as we move down the line. The only thing you might wonder is why NCX? But before we get there, let's look at some statistics. One of them you definitely need to know because it's the same vocabulary term that we learned in a prior lesson. That's the expected value or the expected mean. And so there's our mu again. And this time, instead of having to figure out the expected value or the expected mean by using a sigma notation, where then we would have to say, well, gee, what's the probability of rolling 0 successes? Okay, well, now take 0 and multiply that by its probability, and now let's add it to one success of the 5 rolls, and then what was its probability, and then what was the probability of actually giving 2 successful rolls and multiplying its probability. I don't have to do all that work. This one's got a much nicer formula. All I need to do is take the number of trials, in my example, 5 rolls of the die, and multiply by the success rate, which in this case would have been 1/6. So for my example, I would expect a value if I kept doing this over and over again. When I mean by over and over again, I mean I'm going to roll a die 5 times. Let's write down how many successes of rolling a 1 did I get. Maybe I didn't get any, so I put 0 down. All right, then the next time I might say, okay, I do the 5 die again, and I got 3 of them to come up as 1s. And then the next time again after that, I would say I only had 2 of them. And the next time after that, I would have 0. And then maybe I have another 0, and then I have 1. But I'm still always rolling 5 die at the time, and then just counting up how many successes, or in this case, how many 1s actually came up. And again, this average is supposed to eventually get closer and closer to the expected value. And so in my case, it would have been 5 times 1/6, which would be 5/6. Well, again, we'll get to all that kind of practice soon enough. There are 2 more vocabulary terms that I want to bring up because we talked about them in algebra class. They are variance and the square root of variance, which is known as standard deviation. These are measures of spread. And the neat thing about variance is that it's actually the expected value formula with 1 extra multiplication. You multiply that number by the probability of failure. So that's why I wrote n times s times f, or you could simply just say n times s times not successful, which is again a not situation, which would be failure. And standard deviation is the square root of variance. Now, these two statistics, variance and standard deviation, is not a focus of this particular lesson, but expected value is. Let's take a deep dive into a binomial experiment with the following example. With normal use, a fixture bulb has a 95% chance of lasting for 2 years. So 19 out of every 20 bulbs, I'm expecting that they will work all 2 years. Now let's say I have a light fixture and it has 4 bulbs. What's the probability that blank bulbs last the 2 years? Now first, I wanted to be clear that I am implying that we're talking about an exact number. So exactly 2 bulbs, exactly 4 bulbs. And that actually leads to my first thing. Let's write out all the possible outcomes in terms of how many bulbs will last the full 2 years. All 4 could last all 2 years. Maybe none of them last all 2 years. But I also could have 1, I could have 2, I could have 3. And each of these is going to is representing an exact category. This number represents the 95% chance of lasting. Well, to me, that's a success. So I'm going to call that 0.95, which means failure, which is a complementary event, is 1 minus the probability of success, or in this case, 1 minus 0.95, or we'll just simply call it 0.05. Okay. What I'm going to do is I'm going to take this very important piece of information right here, f plus s equals 1. I know that that means I'm exhausting the whole sample space. Well, with a little bit of math and knowledge from one of the last lessons we did, if I take f plus s and I raise it to the 4th power, and in this case it's because I have 4 bulbs, I also know that 1 will be raised to the 4th, which means it will still equal 1. It is the f plus s raised to the 4th, which is actually the basis of how I'm going to compute each of these probabilities. Of course, it helps if I actually write f plus s and then raise it to the 4th power. So let's go ahead and expand this binomial, and I'll show you how each of these terms match up to each of these particular columns. First off, we're going to need to remember that we'll write down Pascal's triangle, so we're going to go 1. But how did I actually get the 1? Well, the 1 actually comes from going 4C0. The 4 here is because I go 4C1. Then comes 4C2, 4C3, and finally 4C4. As I said, those numbers are 1, 4, 6, 4, and 1. Now, the reason this is a big deal is 4C0 tells me the number of ways I can have 0 bulbs correct in the group, or 0 bulbs work, or successful, or however you want to say it. Because in this case, the only way that I can have 0 bulbs be successful is if I have all failures, and I can only write one way. The 4C1, or 4, represents all the different combinations of how I can have 1 bulb be successful and 4 be failures. Maybe the one on the left is the most successful. It's the only one that lasts all 2 years. Maybe it's the second one. Oops. Helps if I write FS, FF. Maybe it's the third bulb, FF, SF. Maybe it's the 4th bulb, FF, FS. I don't want to have to keep writing out all the different combinations. Because let's be honest here, before I go any further than that, we need to go back and even to our multiplication counting principle and realize we have 4 bulbs, and each of those bulbs have 2 options. It's either failure or success. And it's going to happen all the way down the line. So that means I would have 2 to the 4th, or 16 different possible ways of having the bulbs play themselves out. And so I already got 5 of them here. Here's where I'm going to get the other 11. And 6 are going to fall here. And that would go success, success, failure, failure. Success, failure, success, failure. Success, failure, failure, success. And literally, I could just invert all the letters. FF, SS, FS, FS, or FS, SF. And that's how I'm going to get all 6 possibilities. this is going to be a lot easier if I just say, hey, 4C2 and just figure out the 6 instead of actually having to literally work out all 6. Well, 4C3 is the same as 4C1, so it means there's 4 ways, and that's because if I also invert all these and I simply go F, S, 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 or S, F, S, S, or I go S, S, F, S, or finally S, 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 F, again, I can have 4 ways where exactly 3 bulbs will be successful for the 2 years. And finally, if I completely invert all the failures to successes, I only get 1 way where I can select 4. So here's the 16 different ways I could have, quote, answered the test or laid out the bulbs or all the different patterns. Of that, there is 4 that are all part of the same kind of group, but I need to recognize there are 4 of them. There's 6 here, there's 4 here, and there's only 1 at the end. But I'm accounting for all 16. And because f plus s raised to the 4th equals 1, when I'm done with all these probabilities, this better equal 1 so that I can truly say I've exhausted my whole sample space. That's why we do NCX up here. That's this part right there. Now, if I look at the FFFF, what you're realizing is that that's failure occurring, in this case, 4 times, which means I'm going to be multiplying failure by another failure, by another failure, by another failure, which means I'm going to take 0.05 and raise it to the 4th power. Well, every time I expand the binomial, this degree went down by 1. And that makes sense. If I have 3 failures, I would have 1 success. 2 failures means 2 successes. 1 failure means 3 successes. And then technically, f to the 0 means I had no failures, which means they were all successes. As the failures are going down, the successes are going up. So this becomes s to the 0 here, s to the 1st here, s to the 2nd here, s to the 3rd here, and s to the 4th. Now, I don't need to write down 0.95 raised to the 0, because that technically is a 1, and that would be just irrelevant. But then again, I wrote that one too. So I did that. When I multiply these together, I got on the calculator that this worked out to be 6.25 times 10 to the negative 6th power. Or if you want to write it out, you could say 0.00000. Now I come to my 6th place after the decimal, and I will write 625. That's the probability. And if that's tens, hundreds, thousands, 10,000, 100,000, we're saying a little over 6 out of every 1 million times I do this, I should see all the bulbs burned out. Now, that doesn't mean it's impossible, but it's very, very, very rare. Let's take a look at what happens when we do exactly 1 bulb. You'll see that in every one of these situations, I have this one, I have this one, I have this one, and this one, I always have failure being multiplied by itself 3 times. So let's go ahead and raise it to the 3rd power. I will also need to multiply by success, 0.95, but I only need to do that once. So if you're like doing this work over here, like the multiplication counting principle, you would have had to say, well, that was 0.05 times 0.05 times 0.05 times 0.95, and that would be this work here. But then I would have to, add it to this probability and this probability and this probability, and that's why I have 4 of those same exact matching probabilities. And when I did the math for this one, the math worked out to be let's put that in black, 4.75 times 10 to the negative 4th, or 0.123, and then we'll put our 475. And since that's tens, hundreds, thousands, 10,000s, 4 out of every 10,000 sets of 4 bulbs tested over 2 years would only 1 be working when it's done. Again, not very likely to occur, but more likely than this situation. And we're just going to keep doing this. And basically, we take our expanded binomial and we just fill in the failures and successes, and that's all it takes to actually do this binomial experiment. So here we go. We're going to take 0.05, and we see that it happened twice here, and happened twice here, and happened twice. So eventually, it's going to be 0.05 times another 0.05 somewhere, as well as being multiplied by 0.95 times another 0.95. And this happens not once, but 5 other times for a total of 6 times, hence the 6. And the math for this one works out to be 0, let's actually just move it down here, 0.0135375, or literally over 1% of the time. So somewhere like over about 1/100, between 1 out of 100 or 2 out of 100 times we run this experiment, we should get exactly 2 bulbs to be good and 2 bulbs to be bad. We're going to finish this up. 0.05 is going to be raised to the 3rd power because, I went backwards. Let's try it again. 0.05 is raised to the 1st power. It's the successes, 0.95, that's raised to the 3rd power because it's a success that happens 3 times. And when we mathematically do that, we come up with 0.171475. That's slightly larger than 0.16 repeating, which means it's slightly larger than 1 out of every 6 times. So if I had 6 different families that all used the same bulbs for 2 years for their one fixture that had 4, and all of the bulbs are supposed to act the same way, I would expect maybe one of those families to have 3 bulbs working and 1 dead after the 2 years, and the other remaining amount, well, would fit here, but those numbers are so small, it's all going to probably be over here. And so let's go figure out that last probability, which in this case is 0.05 raised to the 0. Just like I don't need to write this one here, I really don't need to write this one here, because in the end, it's just literally 0.95 times 0.95 times 0.95 times 0.95, or we can just shorthand it and say 0.95 raised to the 4th. And when you work that out, it occurs over 81% of the time, specifically 0.81450625. And if you add up all these probabilities, so if we go and add that one up, 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 you're going to find out that it should equal 1 when you're done, which means we've exhausted all the sample space. There's no overlap. We've got everything covered. And now we can take this information and answer the next question, which simply says, what's the probability that at least 3 bulbs last? So it's no longer an exact situation. It could be exactly 3. It could be exactly 4. And so what we want to do is we want to add those probabilities together. We want to take the probability of exactly 3 and add it to the probability of exactly 4. And so we'll take 0.171475, add it to 0.81450625. I did this before. I hope I can read my handwriting from before. 0.98598125. 0.985988125. Yeah, that's way too precise. So I'm just going to say roughly 98.6% of the time, I would expect at least 3 or 4 bulbs to work after the 2-year span. Our last problem for this particular example is okay, so I've done this experiment. And I found 4 bulbs. And I did this experiment again, and I did 4 bulbs. And then did this experiment again, and I got 3 bulbs. And then it went 4 and 4 and 3 and 4, 4, 4, 4, 4, and a 3. And all of a sudden, somewhere down the road, there's a 2. And if I do this a lot of times, I mean, we just keep running the simulation over and over and over again, I might get a 0. I mean, it's really rare to get a 0, but I might get a 0. There's a better chance I'll get a 1 before I'll get a 0. But most of them, 81% of the time, it's going to be 4s and a lot of 3s. Okay, what should I expect to be my average? It's actually really simple, okay? It's really simple. You do not, emphasize this, you do not have to do the following. You don't have to say, why don't we take 0, because we're finding our mu, and multiply it by 0.000000625. And I am doing this because I am reminding you that this is something that you may have to do when it's not a binomial experiment. And then add it to 1 times the probability, which is 0.0004 0.475, and add it to the probability of 2 occurring, 0.0135375, and adding that to 3 times 0.171475, and adding it to 4 times 0.81450625. That is the long way of doing it, and I am telling you, you don't have to do that, because it is as simple as taking the number of times that we're running the trial, which in this case is 4 separate bulbs. So I'm literally going to take 4 bulbs, and I'm going to multiply it by the probability of success. And each bulb has a success of 0.95. And so when I do this over and over again, and I average all those out, most of the time it should come out to be an average of 3.8 bulbs were successful over the 2-year span. And that is a binomial experiment. Our second and final example for a binomial experiment will be revisiting the 15-question PAGE, which you might recall happened to be in a prior lesson where I basically set up a multiple choice test. I did not give what the questions were, but I still wanted them to answer from 5 choices with only 1 being correct, which basically means they were just randomly guessing the answers. And what I'm interested in is trying to figure out what is the probability of at least 12 correct on this particular test. And then we'll find out what's the probability of getting 0 right out of 15, and then we'll choose a number down here for another one more example. So first off, the fact that if there is 5 choices and success only occurs 1 time, I would expect that probability to be 0.2. Failure, on the other hand, will occur 4 out of every 5 times, which is the same as 80% or 0.8. Now for this problem, I should be writing out, if I'm doing this as a probability distribution table, I should be writing out that I could have 0 correct, 1 correct, 2 correct, all the way up to 15 correct. And that would mean that if I was trying to expand this binomial, because it really is the same work as taking f plus s raised to the 15th power, and you would realize that that would be 16 terms. For that means for me to actually figure out how to get my, quote, 1, because f plus s equals 1, and 1 raised to the 15th is 1, and that exhausts the sample space. That's great, but what am I really trying to accomplish? In this case, I'm trying to find, in my first problem, what's the probability of at least 12 correct? So I really just need to know what the probability of 12 is. Just really need to know what the probability of 13 is, the probability of 14, and the probability of 15. So that's why my table up here is only going to focus on those 4. And I don't need to do all that from the very beginning, because I just have to remember that 15C12 represents all the number of combinations where I have a group of 12 questions being correct and 3 being wrong. So I could do this as 15C12, I could focus on 15C3. Either way, the number worked out to be 455 different ways of doing this. And that is why I'm not going to go ahead and write out all the different ways like I did in the prior problem. There's 455 different ways. Now, if I do my binomial expansions, which is a way I kind of prefer doing this, then I know this is going to have to be 15C13, which works out to be 105 ways. 15C14, now this one I didn't need a calculator, because 15C14 means 14 right and 1 wrong, and when there's only 1, I know that would be the same as how many choices I had, which in this case, choices being how many questions, how many trials I had, 15. And I also know that 15C15 is the same as 15C0, which means there's exactly 1 way of doing it. All successes across the board. Then what I'm going to want to do is I'm going to want to take my failures and realize that I'm going to have 3 failures in this probability. And that means 0.8 is going to be multiplied by 0.8. They're just going to get multiplied by 0.8. They may not be back to back, but they will be multiplied eventually together. So that's why we do raise it to the 3rd power, and I'll say 0.8 raised to the 3rd. Again, I'm going to go across, because now that I know that I have 13 right, I will have 2 failures that need to be multiplied together, so 0.8 to the 2nd, And I really do like seeing a pattern, which is why I'm going to go 0.8 raised to the first here. And it's that same reason for enjoying and seeing a pattern, establishing my understanding, is I'm going to still write down 0.8 raised to the 0, even though I know that number being raised to 0 is going to be 1, and I really didn't need to write that down. Here, when I know that I had 12 questions correct, I'm going to take 0.2 and I'm going to raise it to the 12th power. I'm going to take s to the 13th and take 0.2, raise it to the 13th power. With 14 correct, 0.2 will be raised to the 14th power. And finally, with all the questions correct, 0.2 would have to happen 15 times in a row, so we'll multiply 0.2 by itself 15 times. Well, I have done all this math on the calculator, and I'm going to share with you the results. And some very interesting things happen. First off, 9.5420 times 10 to the negative 7 shows up. And that already tells me something kind of important, that this probability is actually harder to accomplish than it was to get all 4 bulbs to be bad in a 2-year span. So that's kind of, well, that's pretty impressive. And I'm going to go ahead and write this out to 11 decimal places, and I need 11 decimal places, especially when I get to the last one. So when you see times 10 to the negative 7th, that means 6 zeros after the decimal place, and then in the 7th spot, go ahead and write 9542. And just to remind you, that's tens, hundreds, thousands, 10,000, 100,000, millions. That's 9.5 over 10 million. That's close enough to being 1 over a million to, you know, at least give you a perspective. The next number that I found on the calculator worked out to be 5.5050 times 10 to the negative 8. And that means to get exactly 13 right is actually going to be harder, although that shouldn't really shock you, than getting exactly 12 right. And that was such a small probability. This one is even more so. So I'm going to fill in 7 zeros, so that in the 8th space I can put my 5, my 0, and my 5. And I said I'm going to go 11 decimal places. If I do the next one, I found us as to be 1.9661 times 10 to the negative 9th. So 1, 2, 3, 4, 5, 6, 7, 8, and then I'll go 197 and round that out. And finally, to get exactly 15 out of 15 right, it is 3.2768 times 10 to the negative 11th. And that's why I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. I said 8. There you go. 9, 10. And then I'm going to put my 3 down. That is how many decimal places I needed just so I can show you an actual probability for exactly 15 right. And that's tens, hundreds, thousands, 10,000s, hundreds, millions. Let's see what I said, millions there, 10 millions, 100 millions, billions, 10 billions, 3 100 billionths of a time. It is not likely to happen. And again, just make sure that you realize that there's supposed to be a 0 there. So when I actually added up all these probabilities, I took this probability and that probability, and I'm sorry, this probability and that probability and that probability and that probability, it worked out to be 1.01125 times 10 to the negative 6, and that is roughly the same as 0.12345, and then I'll just go 101125. And in this particular case, tens, hundreds, thousands, 10,000s, 100,000, 1 millionth, which is actually mostly coming from the 12 exactly right. But I am actually now over a 1 in 1 million chance of getting at least 12 out of 15 right. Ooh, I feel so much better. Let's go look at a couple more examples. In this case, I want to do a perfect, imperfect 0 out of 15. And hopefully at this point, you realize that you're supposed to go 15C0. And 15C0, we know, is to be the same as 1, because there's only one way to get them all incorrect. Then I have to realize that my failure is going to happen 15 times in a row, so it's going to be 0.8 raised to the 15th. And then finally, I'm going to go success is going to be raised 0 times, because there not once is that going to happen. And so you don't really need to write down 0.2 raised to 0, but in the end, this does work out to be 0.03518. So you do have a 3.5% chance of getting all the questions wrong. And that's actually over, it's getting close to like 1 out of 25, it's 1 out of 30, some kind of numbers like that. So, in a classroom, if I did this, I might expect at least one student to maybe get all 15 questions wrong. I finally did one more from another time, and I decided, you know what, I didn't get exactly half of them right, because there's no way you can actually get half of them right, because that would be 7.5. And so one of my students, once upon a time, got as many as 7 correct. So what we're going to do is we're going to figure that out. And the neat thing about that one is at this point, I hope you understand that for that, all I need to do is think of it as 15C7. Now, again, you could think of that as 15C8 if you really wish to do so. Just realize that the number of failures you have is going to be 8, and the number of successes you're going to have is going to be 7. Now, if I go down here and I look at my calculator, and I see that 15C7 is the same as having 6,435 different ways of writing out 7 correct and 8 wrong. I don't plan on doing that, but I will then take that number and multiply it by 0.8, which will have occurred 8 times. So let's multiply that by, or raise that to the 8th power. And then I take success, which is 0.2, and realize it gets raised to the 7th power. And so when I work that on the calculator, I get 0.013819, or 1.3% chance. So getting 7 correct at least registers, I guess, as a percent, 1%, and it's roughly 1/3 the chance of getting all 15 corrections wrong. Okay, so again, not likely to happen, but you do this enough times, you'll see it. So now comes the last question. What is the expected number, which just means expected value or expected mean? And again, you do not want to go through the whole sigma notation where you say 0 times this probability plus 1 times its probability plus 2 times its probability plus ... plus 7 times this probability plus ... 12 times this probability plus 13 times this probability plus 14 times this probability plus 15 times this probability. That's the sigma notation that we talked about on the last part of this lesson. The beautiful part of this is I just need to realize that if I have 15 questions, my number of questions, I just need to multiply by the probability of being correct or being successful. And so in this case, what is 1/5 of 15? Well, that answer is 3. If I do this over and over and over and over again, and I said, you got 0 right and 1 right and 2 right, and maybe you did get a 9 right, but then I got a lot of 0, 1, 1, 2, a 4, 1, 1, 2, a 3, maybe I get a 6, a 1, 2, 0, 0. There's certain ones that are going to come up way more often than anything else. I don't think I'm going to say 12. I don't think I'm going to say 13. I don't think I'm going to say 14. I don't think I'm going to say 15. I somehow said 9, but all these have a possibility of happening, but if I keep taking all those numbers and actually figuring out what was my average, I would expect 3 to be my expected mean for that particular situation. And that brings us to the end of what is called a binomial experiment. We're going to apply the binomial experiment in our final lesson, which is where we run simulations. And so if you need some more examples, definitely check out that lesson because we'll be referring to binomial experiments a lot.